We're going to spend our whole class today talking about comparison again. We're going to just do a lot of exploring, and I'm going to let you kind of, run with these for a while, and I think some of them will be fairly easy, some will be tougher. We'll just kind of see how it goes. Just a reminder what the direct comparison test is all about. Basically, it's a question of height, right? If you've got a function that's higher than another one, and if one of the other one converges or diverges, you can make a judgment about what you're trying to figure out. So, I mentioned last time, sometimes it's tough to come up with something to compare to, something to kind of pair with. Other times it's not that hard. I would say the one that we did last time would be number one, was probably in the not that difficult category, right? You guys came up with it pretty fast. So that was great. I think you'll find number two to be a little tougher. So I'm thinking, why don't you check this one out? 1 over 2 plus root n. And I'm sure there are many, many, many things to compare this to. It might take some calculator work. It might take some thinking. It might take a little jump in logic. This one will be a little tougher for sure than number one. So, kind of got the basics with number one. This one a little more advanced. Give it a shot. Feel free to discuss, use calculators, ask questions, see how far you get, and we'll check in. How do you know that the red graph here, how do we know that'll measure? P-test, P equals 1/2, which is less than or equal to 1, potentially, right? Yeah, so we do know about the convergence and or divergence in this case of the red graph. So that's good. Now let's see if it fulfills the other requirement. Requirements, technically, for this. I'm going to set my window up here. Ooh, that's not what I want at all. Let's go, yeah. Let's go zoom 6, and just, well, no, I don't want zoom 6 either. Let's go like 0 to 20, and scale that, and y-min, let's go, I don't know, 0 to 2? Maybe that'll give us a good look. Okay, so let's remember the blue graph is the one that we're trying to make a judgment about, and the red graph is the one we're going to try to use to compare. Does that make sense? Okay, so hit graph with hopefully my good window. Okay, so I put my window out to like 20, didn't I, or something like that? So remember, the blue graph is the one that we are trying to decide to convert to diverge. The red graph is our comparison series, and we know for sure that the red graph will lead to a diverging answer. So is this going to meet the requirements or the kind of the conditions for comparison? Isn't it sort of backwards? Like the red, if the red was below the blue, then this would work great, wouldn't it? If red was above or below, or eventually got below, then this would work great, because if red diverges and it's below blue, blue has to diverge as well. But just because the red diverges doesn't mean that the blue will diverge. Right? It may or may not. We don't know. Maybe it's a question of window size. Maybe instead of 0 to 20, maybe we need to do like 0 to 100. Maybe something like that. So 0 to 100, does that red graph ever seem to get below the blue graph? Doesn't seem to. We could probably look at a table and see the differences in the numbers. Does it seem like it's ever going to have the red graph drop below the blue graph? I think if you did enough investigating, at least you could have a decent sense that either it doesn't, or I may or may not ever find it if it does. Does that make sense? So I think that's a really happy mistake. Seriously, thank you for suggesting that. I think this brings in the conditions really well. So that, I think that's an intelligent choice, but it's not the right one for this series. Let me ask it like this. How about this? No, I don't want to ask that. I'll ask that later. I'll ask that one later. Question, John, or a thought?
Yeah, I was going to suggest use
1 over n plus 2. Okay, let's find out. So you guys okay with moving on from this one, just to see if this other suggestion works? Right, yeah, that was our comparison series. Yep. Okay, so Dylan says, I do not want to use 1 over root x because it didn't work the way we wanted it to. So how about 1 over parentheses x plus or n plus 2? So let's do some analysis at the start. 1 over n plus 2, like sigma of that. First of all, we got to answer the question, do we have any idea whether that comparison series converges or diverges? Because if we don't, it's sort of a waste of time, right? We say we do know. What do we think that that does? Diverges why? Well said. Or you could say integral test, right? You could do that too, and there'll be other ones later we could use with that. So I agree. We do know about the convergence or divergence of that. This is not the one that I had in my mind. But there's more than one way to do this, and so let's see if this works. I don't know. We'll find out. So let me go back to my original window. I'll go 0 to 20, and let's see what we get. Okay, so, much closer. So the blue graph is the one we're trying to make a judgment on, and the red graph is our point of comparison, right? So when you look at this, the first condition of, do we know anything about the red graph? That was met, right? We know that the red graph will lead to a diverging answer. Does the graph of the two series up there meet the other condition? Are we going to be able to make a judgment here? Yes. This is a good comparison. Well done. I think what this takes is a little intuition and really a limited menu of things you could even use, because we really don't know much about convergence and divergence about too many things yet. And then maybe a little exploration on the calculator. I like it. So where exactly do these intersect? Obviously there's an intersection point. Did you find that, Dylan? Well, let's see here. Looks like there might be 2 intersection points, actually. Looking at the graph there. So let's see here. If we go back to this. Sure. They both intersect. They for sure intersect at x is 1. Yeah. Okay. So let's see here. I'm gonna bring up another thought here in a second, but let's run with what Dylan said. So, based on that evidence, let's list some stuff out here, right? Let's write this out. So let's go ahead and write out the relationship first. I can say this. 0 is less than 1 over n plus 2, which is less than or equal to 1 over 2 plus root n on what interval? Not 0 to 1. I think it's the 1 to infinity, and I think it is a 1. That's where they actually crossed. So on 1 to infinity. So that interval is within our sigma's domain. Yes?
If we don't know when they intersect, but we know the end behavior, we don't want.
Right. Let's explore that a little further. Yeah, well, let's talk about that a little bit more, because we can navigate our way through that possibly, depending on what kind of technology we have or not. Right? Okay, so let's finish this out. And then I do want to talk about a few other things, one of which maybe would be what Nick just brought up. Okay, so are you okay with that relationship? We can see that from the graph, right? We could make a table and see that as well, I suppose. Okay, and we also have to mention that we know about this, sigma from 1 to infinity of 1 over n plus 2 does what? Diverges, and honestly, if we wanted to be really brief about this, all we have to do is put one word to give a reason for why that series diverges. Harmonic. That's all you got to put. Or you could just put it's harmonic, and they all diverge. All the harmonic series diverge. Okay, so then we can, I think, just go straight to our therefore. Therefore, that original series, what we were looking at in the beginning, also diverges. Oops. And so our overall reasoning here would be based on comparison or direct comparison We could put that there as well. Okay. So Nick, I'm wondering, did you come up with a different comparison series, and is that kind of motivating your question?
Well, I was just curious. Well, I guess for the next one, it wouldn't apply because it's not one because they intersect.
Okay.
I thought.
Okay.
So, I mean, it's just kind of painful to find an intersect, and if you just
I understand.
put a constant down the line, you begin to mean it, they could be fine.
So yeah, I think it depends on the technology that you have. So I'm going to bring one up here in a second that, like with this same one, that kind of gets at your point as well. I think if you could say, hey, at some point within the domain, like the domain for this one was 1 to infinity. So like we talked about on Friday, what if you find that, for some number bigger than 1 to infinity, we have this certain behavior, right? I think based on the tools that you have, that would be acceptable, right? Instead of, you might not be able to say, well, it was actually 3.07 versus, there was some number bigger than 1 within the domain, and from there on out, we have this pattern. I think we're good. I think we're good. Colin.
I don't know if this is what he was asking, but like how what was it? I think it was the blue graph starts above it and then it gets below it.
Yeah.
So is that what he's talking about? Like,
Sorta. Yeah. So let me here.
How do we know that area is going to be even or equal?
So the short answer is it doesn't matter because our series starts at 1, and anything that happens prior to 1 really doesn't matter.
So that's where you're saying if the intersection point was at 2 or whatever.
Yeah.
But could we just pick a different one? Like
So
over x plus 1?
let's talk about that. So here is the one that came to my mind. Like I thought about this one briefly on Friday afternoon because Nick and Josiah were like, what should we do? What should we try? And so I was like, oh, well, what would I do? So I sat down and I figured a few things out, and here's what I came up with. So check this out. And it's really not that much different than what Dylan did. It's simpler. Doesn't mean it's better. In fact, in some ways, his is better. But they both accomplish the same thing. Here's what I came up with. You watching? Instead of 1 over x plus 2, I just did 1 over x. So check this out. This does bring up a few other interesting issues.
Will you please send Jake Patterson to the front desk in
Bring
the
his car
academic
keys?
building and have him bring his car keys?
Oh, I knew it.
My brother has the car.
You should get some bonus points.
I'll just go tell them, I don't even have my car.
Yeah, you gotta do what you gotta do.
I'll
You know what? Can I just tell him that it's paid?
Yeah, just tell them that he has a car.
Hi, Jake said that his brother Cade is the one that parked the car and has the car keys. So if you could maybe have him.
Sounds great, thank you.
She heard all that. That was really good. It's like she was waiting for us. Is she still listening? All right. So let's think about this. This one is a tad different. I want you to notice something here. And gosh, let's see here. So I'm going to compare to sigma 1 over x. So can you guys see how my red graph for a ways there, right? From like 0 to, I don't know, about 4. You see how my red graph is actually higher? So my series starts at 1, and so somebody could look at this and really have an issue, and this is kind of what was brought up was, let me get in the right spot here. 1. So you got all of this stuff right here where my comparison is kind of in the wrong spot, right? Totally in the wrong spot. But whenever I get to this point, which, yeah, it's not I don't think it's a very nice number. So Nick, this kind of goes to your thought. That intersection point doesn't look very good, at least not very integer-like.
Wouldn't it be at 4?
Sorry?
Wouldn't it be exactly 4?
I don't know, is it? Oh, it is 4, never mind. I just was looking at it.
It does look funny.
It looks not so good. Okay, it's 4. But if I did, if I did 1 over x plus 1, that would be a bad one, right? Anyways. So maybe you figure that out, maybe you don't. It wouldn't matter too much. This one we actually can, so this will work out a little nicer. So check this out. I could say this. 0 is less than 1 over x, which is less than or n, I guess, which is less than or equal to 1 over 2 plus root n, on which interval?
4 to infinity.
4 to infinity. Right? I can't say 1 to infinity because that's not even true. But I could say 4 to infinity. So keep going here. I can also say sigma from 1 to infinity of 1 over n diverges because of either harmonic or p-test, whatever I want. So I can make a conclusion, therefore, the original series also diverges by comparison. Here's the thing to think about. That purple area that I have up there, it's a finite area, right? And we're talking about long-term behavior, like what's happening as we go way to the right edge of the graph. That little sliver of actual, numerical, like real numbers, really not going to matter that much as n gets closer and closer to infinity. It's no comparison to infinity, if you will. So, yeah.
So what if that area was also infinite? Like it was like 10 plus?
Well, yeah, like if you had a vertical asymptote, well, then we wouldn't really have a series starting there then, right? Because like a series, like the terms are actual terms, right? They're not like, well, the first term was infinity. Does that make sense?
Yeah.
So if it were, I would say we need to start our series at a different n value. It just means that we maybe made a little error on our n equals to start off. Maybe we should have been like, hey, let's start it at 3 instead of 1, right? Instead of the thing that caused the issue. It would more be just like a typo. Yeah.
So when you're stating the interval, like you did for infinity, of where it's
Yeah.
less, does it have to be, like this might be a silly question, but like right at the point, like if there's like.
It has to be contained within the interval of the original
Well, like,
series.
could you say like 5, like say the point is like it's more work to find the exact point, but you know that let's
Yeah.
say like 5.
I agree. And that was my thought. Like I said, when I compared my idea to Dylan's, I thought, it occurred to me because it was really simple. I'm like, 1 over n, I know a lot about that. Would that work? Oh, look, it worked.
Okay.
Dylan did a little more work, and he's like, well, how could I get them to intersect right in the same spot, right? And you did it, and that's awesome. And so it really tidied things up very nicely for what he did, but we didn't have to do it that way.
So you can.
As long as it's a subset of the domain of the original series, that's really all that matters.
Sure.
Well, as long as that subset also contains,
Yeah.
goes towards infinity,
Yeah.
right? It's not just like a little tiny chunk. It has to be that long-term behavior.
Thanks.
Yeah. Other questions? Yeah, please.
Could you do, like, if there were a circumstance where a constant would always be less, could you do, like, a constant? Like, could you do, like, 1/8 or something?
Okay.
And, like, what would the end behavior of a constant be?
It diverge, right? Because your nth term would be 1/8,
Oh, right, okay, yeah.
right? The hard part about that is, I don't think you can do that though. Because at some point way out there somewhere, that 1/8 would eventually be higher. Because right, 1 over 2 plus root n, like if you did the nth term test on the original series, so if you did limit as n goes towards infinity of 1 over 2 plus root n,
Oh,
aren't we heading towards 0?
right.
So
yeah.
eventually that 1/8 would be too high and our comparison would be out of whack. It'd be backwards. So yeah, whatever you compare to has to be some kind of a nicely decreasing, similarly decreasing function. Good question. Nobody's ever asked that one, but makes sense. All right, so if you haven't already taken a peek at number 3, please do take a peek at number 3. Okay, so similarly, feel free to use your calculator to do some comparing and graphical looks and decide what you want to try to compare to.
I have a good one, but it's
Sorry, I don't know if mine works.
What do you guys think?
it works.
Dylan, you think you got another one?
1 over x cubed.
Okay. So here's what Dylan proposed. He says 1 over x cubed. So I'll just make a note of that and say we're going to compare to this. Okay. So guys, remember, here are your conditions. In order for this to make any sense at all, you need to know about the convergence or divergence of your comparison. Do we know about that one?
Yes.
We do. So we'll get to that later, but we do for sure know about that. And then also, well, actually, let's go there now. This will make this next part a little bit easier. Does that series converge or diverge?
Convergence.
Okay, so we could say this series converges because of what?
P-test.
Yeah, p-test, and we got to explain a little bit about the p-test.
Equals.
And who cares about that? It's bigger than 1. So guys, this is good practice with that p-test. You want to make sure that you are telling me why. Remember, the idea is all of these are either going to converge or diverge. And so the fact that you picked one of the two doesn't really matter. It's really about your reasoning. So make sure you're giving a good explanation. Okay, so if that's the case, then hopefully this is true. Is that true? For an interval that we care about. I think so, right? I mean, if you think about this is the way that I think about it. Isn't this denominator always 1 bigger than that denominator?
Yes.
And if the denominator is always 1 bigger than this other denominator, then the whole fraction is always just like a tiny bit less than the other fraction. So I that's how I think about it. Seems like maybe you guys are too. So this is true on what interval? From somewhere to infinity, right? Where does that start? Where does that relationship begin? Does it start at 1?
Nope. Just kidding.
Well,
Wait,
so-
no, yeah.
I think it does, because if you plug in a 1,
It works.
Then it
out.
would be
1 over 1 cubed plus 1 would be 1/2, which is less than 1 over 1, which is 1. Sure. So I think this works. Did you see it on the graph too? Okay. So we can say, therefore, the original series also converges. Converges. Comparison. Okay, did anybody come up with a different comparison? I know Cole came up with 1 over n squared, which worked just fine.
1 over n would work, right? Wouldn't it?
I don't think so, because 1 over n
Oh,
diverges, and so we'd have to flip around this,
right.
and then I think we'd find out that it didn't do what we thought it was going to do. Yeah. Anybody try a different one? There's more than one way to do this. This was, to me, was the most obvious way. Doesn't mean it's the best, but
Tried a different one.
whatever.
Didn't work.
Okay. All right. So then I want to share with you guys a little bit of something else. Guys, this is new and different, and I really like this one. There we go. This has not always been on the AP framework. Hey guys, listen please. This maybe give you some insight as to how cool this one is. This one has not always been on the AP framework. It showed up, I want to say 2 years ago. But I have always taught this in spite of the fact that it's not on the AP framework. Because once you get this, especially like on a multiple choice, it's like magic. It makes things that would normally have been really tough, really easy. Okay, so I taught this for a long time simply because it makes things easier if just doing some really basic convergence divergence. Okay, so this is called the limit comparison test. And as you probably can glean from the name, it involves comparison and a limit. Okay, that's it. So they weren't very creative when they named this thing. And so I put this point up here, and I think you guys have experienced this a little bit already. Sometimes it can be very difficult to find a comparison. That one we started off with today, kind of difficult. And so I'm thinking if you were going to try to deal with that first one and you spend a couple minutes, you're like, oh man, I don't really have anything to compare this to. Maybe at some point you'd be like, oh, that limit comparison thing would be easier. And I think you'd find that in this case it would be a lot easier. So we'll use the limit comparison test in these cases. Please note the conditions here. It comes up every now and then. The conditions are the two series that we're dealing with, both the one that we're trying to figure out and the one that we're comparing to, have to be positive. We're going to find out in the next little section of our notes packet that when the signs start going plus, minus, some interesting things happen that kind of mess this one up. Okay, so the terms have to be positive for our series, both of them. And if that's the case, if I do the limit as n approaches infinity of one series over the other, and the order doesn't really matter on the division. You can put a over b or b over a. It really doesn't matter. If you get a number over here that is finite and positive, so in other words, it's not infinity, and it's not 0, and it's not negative, right? Finite and positive, then both series will do the same thing as far as convergence or divergence. Okay? The key is to pick a positive series that you know about. We've already had some practice with that, like with our direct comparison that we just did. And then here's one. To me, this is the key to making this super easy. Whatever you compare to has to have the same relative magnitude as the series you are testing. I'll kind of explain what that is here in a second. And then I put a note here. If you can't figure out the comparison, it can be super effective. Okay. So I want to help you with one or two of these, and I'll let you guys kind of wrap these up. So let's take a look at number one. And I would like to kind of illustrate how number one could go a lot of different ways. So check this out. With number one, it just says use an appropriate test. So let's talk through this first one. For number one, what would the nth term test tell us?
0.
We go to 0, which tells us nothing. So we'd move on. Is number one of those lovely geometric series where if we can just figure out the r, it's over with pretty much? No, it doesn't have the numerical base with a variable exponent, so it's not geometric. Could I do the integral test with number one? Would that be something I could do the integral of pretty easily? Yeah, I could definitely do the integral test there. It's positive, continuous, and decreasing. I can find the integral. That'd be a pretty easy way to go. Is this a p-series?
No.
Why? Plus 5 ruins it, right? Hey, guys, listen. Hey, it is harmonic. So if you wanted to with this one, if you saw this, you could look at it and say, hey, that's a harmonic series, and all the harmonic series diverge. Done. That'd be a pretty fast way as well. So I thought I'd start you off with this one knowing that this one diverges. So let me explain how we would do this. I am going to say that this series right here is positive, and I'm going to come up with a comparison, and here's how I'm going to come up with a comparison. Bless you. Your comparison needs to have the same relative magnitude of degrees as what you're trying to deal with. So, look at this series up here. What's the degree of the numerator? 0. What's the degree of the denominator? 1. And so, whatever I compare this to needs to have a difference in degrees of 1. And there's lots of ways to do that. Couldn't I compare this to, or like those two, and obviously you can see many others would have a difference in degrees, like a relative magnitude of degrees of 1, right? What would be the easiest of that group? 1 over n. Okay, so I won't do any silly ones, but I will say 1 over n is also positive. That meets the conditions. And I also know that sigma 1 over n has what kind of convergence divergence behavior? Diverges. We'll get into that here in a second. So here we go. Here's my limit comparison test. I'm going to write limit as n heads towards infinity. And then I'm just going to make a fraction of my two nth terms. And it really doesn't matter what order you do it. I'll just do it like this. 1 over 2n plus 5 over 1 over n. Limit as n goes to infinity of one of them over the other one. It doesn't matter which one is which. Whenever you have a fraction divided by a fraction, what's that little pattern we use?
Flip.
Yeah, copy dot flip, copy dot flip. So wouldn't this give me n over 2n plus 5? Using the old pre-calc trick, that's 1/2, isn't it? So that number is positive and finite. So here's what that means. Since that limit's result is positive and finite, whatever my 1 over n series does, the one that I'm trying to work with, will do the same thing. Make sense? So I can come over here and conclude and say, because sigma from n equals 1 to infinity of 1 over n diverges, and that would be because it's harmonic maybe, or p equals 1, or p-test, or integral test, whatever you chose to use. The original series also diverges because of limit comparison test. Okay. Questions?
So why did you decide to do that with harmonic?
So remember at this. So you got to suspend your disbelief a little bit. Remember, I ran through all these and I said, could we have done this? No. Could we have done this? Yes. This one, no. This one, yes. And one of the ones that Jasmine brought up, or somebody brought up, said, hey, isn't 1 over 2n plus 5 just a harmonic nth term? And I said, yes. But I said, what if you didn't see it? What else could you do?
Okay.
So you're about to run into one where none of those are going to work at all.
Okay.
So, yeah, I kind of snickered when I wrote it because I'm like, if you recognize that 1 over n is harmonic, why didn't you just recognize that 1 over 2n plus 5 is harmonic to begin with? I get it. But you got to admit, sometimes in the midst of a test when you're like trying to do your best, you end up taking these circuitous routes where you're like, in the end, you're like, oh my gosh, I could have done that in like 1 minute and I took 10 minutes. What was I thinking, right? So maybe you end up doing that. This would just be another path to get there. I don't think you'll find that to be true of 2. I think 2, you'll be kind of painted into a corner. So other thoughts or questions about that? Just wanted to start you off with an easy one that you already knew about that we could compare to. So let me help you get started with 2 and see how this goes for you. If you were going to do the limit comparison test for number 2, what would you compare that to? Liz has it. So guys, this is key to this. You want the difference in the degrees of the top and the bottom to match the difference in degrees of what you see on your series. So our original series is 1 over second degree, or like 0 degree over second degree. And so I want to compare it to something that is 0 degree over second degree. I could compare it to all kinds of unwise things. I think 1 over n squared is the best way. But I mean, you could compare it to this. Right? That has a difference in degree of 2, but that's not very simple. Keep it simple, right? Keep it really simple in things that you know about, like 1 over n squared. Okay, so play around with this a little bit. Please try number 2. I want you to compare it to 1 over n squared. Once you start to get the hang of this, we'll go a little more rapidly. Talk a little bit about how you can go super fast on a basic multiple choice. Remember your conditions. Both your comparison and the original series have to be.
Do you have to prove it positive?
Well, so here's the thing, like how many terms are in the series, right? It'll take you forever. So what all I really want you to do is like notice that all the terms are positive and then just say it. We're not going to go through and like prove every single time. We just want you to
So
say
if it's not, then you couldn't use this.
correct. Whatever you say has to actually be true. But I'm not going to have you go back and like prove every single term or like use like a derivative or something to prove. I just want you to recognize, hopefully it is true, and recognize it and use it. No, all you have to do is just say p equals 2, which is bigger than 1. Is that what you mean by prove it? Yeah. Then yes, you do have to do that. you don't have to go back and reprove the p-test, which would be using an interval test.
So then if L is finite and positive, you should convert this.
If L is finite and positive, that means both series do the same thing.
Oh, okay.
So if your comparison
Oh, and then
diverge,
change it.
then your
Like
series
one
diverges.
brain series. Okay.
Exactly, but if your comparison converges, then your comparison will also.
All right.
No new updates, right?
So based on this test, that means that this highly processed is still not the p-test.
So this is why I always taught this in the past, because like if this were some multiple choice, scenario, and there's always be some of these on there, you could look at this and say, yeah, difference in the degrees is 2, convergence. So the p-test is specifically 1 over n to the p.
I could say 1 over n, or whatever the highest degree of
Well, it's
So if I could get it to like end of one of those.
Right, I understand. So in other words, y isn't stated as such. So what I'm mulling over is, if it's not stated as such, is there contrarian example, right? I can't think of one off the top of my head. I can't think of one off the top of my head, to be honest. I'll have to do some finding on that, right? Why wouldn't it just be broad?
Would it only fly if you say that it dies in
That's what I'm trying, that's what I'm
It could be it, you know, like, like let's say this was like 1 over 3n, 7/8 plus maybe 4n.
You're supposed to be rich.
That, yeah, you certainly can't apply it to that. Maybe it's just because of the one-sidedness of it. Maybe it's twice as stated. I'll do some more.
That's definitely not.
But Nick, you're right, this does run after, like the quick, like intuition that you'll get, you get, converges. You might have to go through like through all the steps or whatever, you know, right now, but you'll know. Yeah. The limit is what? Really improve. That doesn't prove anything. Right. So I would say that, like, it would be perfectly acceptable to just like say limit of, you know, the appropriate fraction equals 1/3. It's easily arrivable at using accepted thought. If you're going to do all that stuff, you darn well better be showing L'Hopital's rule conditions and all that stuff. Yeah. Okay. Hey guys, let's check this one out. This is a good comparison. We would want to say that both of the series that we are considering are both positive. And at least on our interval that we care about. Okay. So then we'd set up our limit comparison. And again, I made a joke about it earlier, but literally it's a limit of a comparison being a fraction. So it'd be the limit as n heads towards infinity, and it would be 1, let's say 1 over n squared over, I think I'm doing this reverse from last time, but it really doesn't matter. This would give me limit as n heads towards infinity, of 3n squared minus 4n plus 5 all over n squared. And again, using the pre-calc trick, this is a pretty simple limit, right? What do I get? I got 3. Anybody else do it like this, or do you all get 1/3? Yeah, so you can be flexible. I mean, it doesn't really matter which one's on top. The point is, this is positive and what? And finite. Okay. So that means, because that number is positive and finite, that means our original series is going to do exactly whatever our comparison did. So I want to say then that sigma of 1 to infinity of 1 over n squared converges because of the p-test. Therefore, my original series also converges. And that is limit comparison test. Okay. What do you guys think? Questions? Okay, continue to try to make some good connections here. If you guys would move on to 3, 4, 5. Do as many of these as you can. You have all the conditions there. We should be able to figure out convergence, divergence fairly quickly.
Kidding me. Come on, Eileen is stuck in my head.
Right now, it's like,
Were you gonna compare? Got him.
1 over root
I
n.
don't know why it's stuck in my head.
Yeah, the only requirement really is that they have to have the same difference in degree. And so 1/2. Yep. And keep it simple, right? Don't be like, I think I'll try one for the square root of this. Yeah. Just keep it really simple.
It's exactly the same. I love that. I need
really nice sticker. Belmont. Oh, a little bit tired. I still don't know. What?
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 What are you talking about?
I thought we were singing thrift shop.
What?
What? Oh.
I've got a serious case of senioritis.
What's that? Is it contagious?
Yeah.
I feel like it's more work to explain it than
Let's run through some of these right here. Guys, I'm going to give you, listen up please. I'm going to give you kind of the Cliff Note version of this because you have some good examples of the conditions above. So again, I want to be really clear about this. What I'm about to show you is just going to be the sparse version. But consider this. Did you guys, for number 3, did you compare to 1 over root n?
Yes.
You can compare to other things, but to me that would be the most convenient. And if you're comparing to 1 over root n, did you not get divergence for the original? Okay. So again, if this is all you wrote on some quiz in the future, you're going to be disappointed. I'm just giving you the quick version because we have like 3 minutes left. You have good examples up above. Number 4. Several people mentioned, man, number 4 looks pretty complicated. The top is a lot more complicated than we're used to. But what's the difference in degrees? So what did you compare to? And when you compared to that, when you did the limit, didn't it turn out really nicely? The pre-calc trick came into play, and you should have gotten convergence because 1 over n cubed also converges. You got that positive finite. You probably got 1/4 or 4 perhaps or something like that? Okay. And then the last one, number 5. A little trickier. What was the difference in degrees? 1.5? 1.5? Yeah. So I would compare this one to 1 over n to the 3/2. Sorry, I don't know what that's all about. I accidentally hit my downloads. And because of that, does 1 over n to the 3/2, does that converge or diverge? That converges because of p-test, therefore my original series, once I get done with all the limit stuff, would also converge as well.
So does this work for everything?
Doesn't work for geometric.
True.
Doesn't work for anything with factorials, which we'll get to later. Does not work for anything that has negative terms.
We haven't gotten to
We'll get to that next. Yeah. So guys, before you go, hey guys, before you go, just a reminder,